In this lesson, we're going to look at lines and planes in space. In the plane, a line is determined by a point and a number giving the slope of the line. In space, a line is determined by a point and a vector giving the direction of the line. Suppose that L is a line in space passing through the point P sub 0, which is at x sub 0, y sub 0, and z sub 0. And our line, L, is parallel to the vector v, such that v is v sub 1 in the I direction, plus v sub 2 in the j direction, and v sub 3 in the k direction. Then L is the set of all points P sub x, y, z. This is the triplet, and these are all points on L, for which P sub 0 P is parallel to V. So let's diagram this out. Here's our z-axis and our y-axis and our x-axis, and we'll label these. Here we go, x, y, and that's our z-axis. And we're going to draw our line L. So here's L. And this line is a line segment. So this is line segment L. And we have a point on line segment L right here, P naught. And if we draw a vector from P naught to another point P on line L, like this, then this line PP naught, or vector PP naught, is parallel to our vector V. And the way to represent parallel is we do arrows like this, and this represents that V, vector V, and P naught P, this vector here, these two vectors are parallel. So if we look at P naught P as a segment, if it is parallel to vector V, then we can say that P naught P as a vector with a magnitude is equal to T, which is a scalar, times vector V. The value of T depends on the location of the point P along the line. Okay, so I shifted this up so I could fit in an expanded form for vector P naught P equal to T V. And it's written, I'll write this in blue, as x minus x naught in the I direction plus y minus y naught in the j direction plus, I got a space here, z minus z naught in the k direction, and that is equal to our t, which is our scalar, times our vector v, which is v1 in the I direction plus v2 j plus v3 k. This can be rewritten as follows: x sub I plus y sub j plus z sub k is equal to x naught I plus y naught, that's sub-zero is naught, j plus z naught k plus t times v1 in the I direction plus v2 in the j direction plus v3 in the k direction. If r of t is the position vector of the point P on the line, and r sub 0 is a position vector of the point P naught, or P sub 0, let's write that out, then the following equation is the vector form, and that is r sub t is equal to r sub naught plus r sub v, and that is for all values of t, all real values of t, where r is the position vector of the point P on the line L, and r naught is the position vector of the point P naught on the line L. Equating the corresponding components of the two sides of the equation gives three scalar equations involving t, and that is x is equal to x sub 0 plus t times v sub 1, y is equal to y sub 0 plus t times v sub 2, and z is equal to z sub 0 plus t times v sub 3. So these three equations, 1, 2, 3, are the parametric equations of the line for values of t from negative infinity to infinity. Okay, so let's try an example of this. Example 1. Let's move that up. Okay, in our example, we need to find the parametric equation for the line through the points through the point negative 2, 4, 2, 0, 4, this is a triplet, which is parallel to the vector v, and the vector v is 2 in the I direction, 4 in the j direction, and negative 2 in the k direction. So let's move that up. Okay, so what we want to do here is we see that our point P sub 0, which is made up of x sub 0, y sub 0, z sub 0, is the point negative 2, 0, 4. And our vector that our line is parallel to, v sub 1 I plus v sub 2 in the j direction plus v sub 2 in the k direction, is equivalent to 2i plus 4j minus 2k. So we're going to use this, let's move that up, to find our answer. And we get x is equal to our x naught, which is negative 2, plus v sub 1, which is 2 times t, and then we have our y is equal to 0 plus 4t And then our z is equal to 4, which is z sub 0, minus 2t. And I move that up. So here's our solution. And I used our formulas for the 3 parametric equations.